Hi, my name is Shanawaz. So far, we have seen that at several instances, one category is included in another. Now, we want to investigate this phenomena more generally. For that, we introduce the notion of subcategories. So, we will start with the definition. So, a category A is said to be a subcategory B. So, this is said to be a subcategory of a category B. Provided the following conditions are satisfied. So these conditions they need to be satisfied. So the condition first is the object class of category A is contained in object class of category B. The second condition is that for each object say A and A prime in the category A, so the other objects the set of morphisms between the objects A and A prime in category A is contained in the set of morphisms between the objects A and A prime. But at this time, they are the morphisms in category B. So this is the second item. So the third item says that for each object A in the category A, the identity element, I mean the identity A in the identity A in the category A is same as 1 sub A in category B. So the identity morphism on A in category A has to be same as the identity morphism on the same object in category B. And finally, the composition law in A. So the composition law in A is the restriction. So this is the restriction of uh, the composition law in B to the morphisms in A. So if these conditions are satisfied, then we say A is a subcategory of B. So one might think of, I mean, if we look at this condition, these two sets they may be equal, but in general they need not be equal. Um, I mean, a subcategory B for a subcategory A or B for which equality shows up here, we call such a subcategory a full subcategory. So it is. So we introduce this with this definition. So let A be a subcategory of a category B. Then A is said to be a full subcategory. So this is said to be a full subcategory if for each objects A and A prime in the object class of A, uh, if we look at the set of morphisms, I mean the set of arrows between objects A and A prime in category A, so it is same as the set of morphisms between the same objects A and A prime but in category B. So such a subcategory is said to be a full subcategory. So uh, one can think of, so if we look at the category of all groups, I mean the category GRP of all groups and the category AB of abelian groups, then this category AB is a full subcategory of GRP because uh, every abelian group is a group. So the object class in AB is contained in the object class in GRP. But if we look at, suppose we have two objects, say A and A prime in AB, so they are abelian groups, and these objects are also there. Now, if we look at the morphisms, which in this case are the group homomorphisms, so if we look at the home set of A and A prime in category AB, this is same as the home set of A and A prime in category GRP because these homomorphisms, these home sets, they have nothing to do with the group being abelian. So we can consider AB as, I mean, a full subcategory of GRP. Now, uh, so because of the nature of full subcategories, a full subcategory of a category B can be determined by specifying its object class within B. So all we need is to specify the object class. So this is a remark. Let us call these remarks. So the first one is, so the nature of um, um, the nature of full subcategories uh, of a category, say B. So we can determine the nature. So this can be determined by specifying its objects. It is object class. So I mean the object class within the category B. So one should also note that, so if we have a functor between two categories, say category A and category B, then image of a category under a functor need not be a category. So the image of a category under a functor need not be a need not be a subcategory. So for example, um, if we consider, so if we consider the functor, suppose we have a functor which takes, suppose object is A and B, I mean, we have a morphism between the objects A and B, and another morphism between objects B prime and say C. Let us call this G. And this functor takes these, I mean, these morphisms like this. So we have Y here, we have X, we have Z here. So this morphism F between object A and B is carried to the morphism P between objects X and Y, and G is carried to the morphism Q. Then by composition, this is the morphism QP. So this functor is defined by, so this functor, let us call this functor F. This functor F carries the object A to object X. It carries the object B and B prime to the same object, say Y. The object C is carried to the object Z. The morphism F is carried to the morphism P, and finally the morphism Q is carried to the morphism, not Q, morphism G is carried to the morphism Q. So then one can notice here these morphisms P and Q, they are I mean, they have the pre-images F and G under the functor F. So this is the functor F here, and QP has no pre-image. I mean, this cannot be a subcategory. So this such a functor, I mean, the image of of such a functor uh, need not be is not a subcategory. So one can note here then P and Q are images of F and G under F respectively, whereas PQ is not. I mean, PQ is not image of any morphism. So this, I mean, the image of this functor need not is not actually I mean, a subcategory. However, if a functor is full functor and or it is injective on the object class, then the image of a category is a subcategory. So this is the third remark here. So one should note here, if we restrict this functor to the object class, so then it is not one because if we look at this, so if B and P prime are distinct objects, then their image is same. So this F is not injective restricted to the object class. So we should write here, however, if F is full, which means it is subjective on, I mean, it is subjective on both classes when restricted to I mean the object class and the set of morphisms, or so if F is full or F is injective um, on objects, then the image of F is a subcategory. Now let us do some examples. We'll start with a trivial example. So if we consider any category A, then the empty category and A itself are always full subcategories of A. So for any category, say A, the empty category and A itself are full subcategories of uh, A. So if we look at, I mean, the category AB of abelian groups is a full subcategory of the category GRP of groups. So this is the category of abelian groups where the morphisms are just group homomorphisms, and this is the category of all groups where the morphisms are group homomorphisms. So one can notice here that this the object class in AB is contained in the object class in GRP. However, the morphism sets in both AB, I mean, for any two objects, say A and A prime in AB, in the morphism set between A and A prime is same as the is same as the morphism set of the same objects A and A prime in the category GRP. So this is a full subcategory. Now there is one more example. So if we consider the category of Hausdorff spaces where the morphisms are continuous maps. So let H house be the category of Hausdorff spaces. Then this house is a full subcategory of uh, top, which is a category of topological spaces. The full subcategory of top of topological spaces. So again, the object class in house is properly contained in the object class in top because every topology need not be a Hausdorff topology, but every Hausdorff topology is of course a topology, but the morphisms in both cases are same. So if we take two Hausdorff spaces, then being two spaces in top, two objects in top, their morphism sets are exactly the same. So this is a full subcategory. Similarly, if we look at the category of so let us write this down here. So the category, let us call this TYCH, Tishnov spaces. So this is the category TYCH of Tishnov spaces, which are the spaces which are T1 and completely regular, i.e. the completely regular T1 spaces. So this category is a full subcategory of house So this is a full subcategory of house. Similarly, if we look at the category of compact house drop spaces, mm, then the compact house drop spaces category of compact house drop spaces is a full subcategory of this category TYCH, partition of spaces. So the category uh, let us call this uh, let us call this HCOM, which means the compact house drop spaces of compact house drop spaces. So this is again a full subcategory of TYCH. So one should note here that every compact house drop space is a TYCH object. I mean, if we take a object here, that means this A is a compact house drop space. So that means this A is also a completely regular T1 space, i.e., this A lies in this object. So the object class in this HCOM is properly contained in the category TYCH. However, the morphisms between if we take two objects here, say in A prime, then the morphism set between these two objects in this category is same as the morphism set of morphisms between the same objects but in this category. So they are exactly the same things. So uh, this HCOM is a full subcategory of TYCH. Now let us do some examples apart from these topological spaces. So let us consider the so this is the category, this is the example fifth. So consider the category, let us call this rel, which means so in this category the objects are uh, the objects are these pairs x and say sigma, where x is any set and this sigma is a binary relation on x. So it's a binary relation on x. And the morphisms here are, so if we take a map f between the object say x sigma uh, and so the and morphisms f from x sigma to say y, let us call this tau. So this sigma is a binary relation on x and tau is a binary relation on y. So this is a morphism if it is the relation preserving uh, map. So and the morphisms f from these two sets are the relation preserving maps. Now what do we mean by relation preserving maps? So that means, so if we have two elements say x and x prime in x such that x is related to x prime via the relation sigma, then their image under f uh, which are the elements in y, so they must be related via the relation tau. So this is what we call a relation preserving map. So now we know what is this category. So the objects here are these odd pairs, x and sigma, these pairs, where x is any set and sigma is a binary relation on x, and the morphisms between objects are the relation preserving maps. So then if we look at so then the I mean if we look at the class of pre-ordered sets, so then the class of pre-ordered sets, pre-ordered sets. Now the pre-ordered sets are the sets which are equipped with a relation which is reflexive and transitive. So these pre-ordered sets, so they are all sets, so class of all pre-ordered sets. So all sets which are equipped with a binary with a binary relation that is reflexive and transitive. So this class of pre-ordered sets, so this yields a full subcategory of rel. So this determines a full subcategory. Let us know this category by say P. P stands for pre-ordered, and S stands for sets. So pre-ordered sets of, so this determines a full subcategory cross of rel. Similarly, now if we look at the all pre-ordered all partially ordered sets, which are the sets equipped with a binary relation which is reflexive and symmetric and transitive, then that class of objects determines a category which is a full subcategory of this pros. So the class of all partially ordered sets, uh, which means um, so i.e. the sets, i.e. all the sets equipped with uh, a relation which is reflexive, antisymmetric, and transitive. So this class of objects also determines a full subcategory. So this determines a full subcategory. Let us call this subcategory, this by POS. So this is a full subcategory of pros, which is the category of pre-ordered sets. Similarly, if we consider the category GRP of groups, so that is a full subcategory of mon, where the category of monoids. So the category GRP of groups is a full subcategory of moon, which is the category of monoids. Now, note that a monoid is a semigroup with unity. So, i.e., semigroups with unity. And the morphisms here are the monoid morphisms, which are the semigroup homomorphisms that preserve the unity. So, and morphisms are monoid homomorphisms, i.e., a semigroup homomorphism which preserve the unity. So, of course, then GRP is uh, a full subcategory of MON, because um, if we look at the object class of GRP, that is the class of groups, and we know every group is a monoid. So, object class in GRP is properly contained in the object class of mon. Similarly, if we look at two objects here, say A and A prime, which are groups. So this is, and we look at this set, which is a home set. And if we look at the home set between these two objects in MON, then they are precisely the same, because every group homomorphism is also I mean, is also a monoid homomorphism. Now, since A and A prime are the same groups here, so a monoid homomorphism between A and A prime is same as a group homomorphism, provided A and A prime are groups. So there is no distinction between these two sets. Now, one might be wondering. So far we have the categories so far we have discussed are all the examples of full subcategory. So one might be thinking, what is the example of a non-full subcategory? So if we look at this category, which is a category of monoids, and if we look at the category, say SGR of semigroups, so then we know the object class in the category mon is properly contained in the object class in SGR, because every monoid is a semigroup. So this is properly contained here. However, if we look at say two monoids, say A and A prime, and we look at the morphism set between these two objects. So this is the morphisms in the category mon. And similarly, if we look at these two objects in SGR as semigroups, and if we look at the morphism set between these two objects in SGR, so they are the semigroup morphisms and they are the monoid homomorphisms. So here one should note that this is proper containment. They are not equal, because these monoid homomorphisms, they are supposed to preserve the identity, the unity. However, a semigroup morphism need not preserve the unity, because uh, unity is not mandatory to be in the objects in semigroups. So This is an example of a non-full subcategory. So this is the ninth example, I think. So the category moon is a non-full subcategory of SGR. I mean the category of all semigroups and all semigroups and all semigroup homomorphisms. So they were there were some examples of full and non-full subcategories.